coding and things like that. So if you can help support Techlahoma, you can check out all the Techlahoma meetups are on the techlahoma.org site. There's also a Techlahoma Help Wanted board, which is just a bunch of like volunteer type tasks that need to get done. So if you're wanting to pitch in, then you can check that board for more ways to help out. There's also some ways you can help financially. So one is if you use Amazon Smile, Techlahoma is on there. So if you use Amazon Smile and you want to set Techlahoma as your charity, you can do that. If you subscribe on Twitch, that helps out. We get some revenue from Twitch if you subscribe there. And then you can donate. There's a donate.techlahoma.org site. Ask your company to sponsor. That always helps. And you can buy some merchandise from the store. Max, is there new merchandise coming? Is that? There will be, yes. There will be new merchandise soon, as I hear from Max. Okay. So, yeah, check out all that stuff to help pitch out or pitch in or help out, help something, do the things with the, give us money. So 36 Degrees North also donates this space for us to meet, and they have a bunch of workshops, and they also do co-working and desk rentals and office rentals here. So check that out. You can check. I can't see who's at the front desk. No one? Oh, who is it? Oh, it's Jamie. Hey, Jamie. So you can talk to Jamie. And you can also check out their calendar. There's a bunch of the Techlahoma meetups that meet here. So Tulsa Data Science and JavaScript, Agile, game developers, Lambda Lunch, UX, they all meet here. So they're on both the Techlahoma calendar and the 36 North calendar. So that's all the regular usuals. Thunder Plains 2018 is coming up. That is November 1st. Right now it's open for sponsors. So if your company likes to sponsor the local and statewide events, this is one of the big ones. So it happens in Oklahoma City on November 1st. Check out the Thunder Plains website for sponsor details. Anyone else? Am I missing anything about Thunder Plains? Anyone know anything else? Okay. I think the CFP is now closed, so they're mostly just sponsors and tickets haven't opened yet. August 24th, Code for Tulsa Criminal Justice Summit. Is Brittany or Carlos, any of the other Code for Tulsa folks here? No. Okay. So so this is going to be at the library. Wait, I saw Kat. Where'd you go? Do you know, are you helping host this? I'm not. Oh, okay. It's at the library. Yes, I was like, it's at the library. How are you not?
It's in Greddington.
Here, come up here and talk about it a little bit.
I know next to nothing about this.
That's okay, so do I.
Okay.
Except that I'm apparently helping with it.
August 24th at, I think, 11 a.m. Yes,
9 a.m. to 1 p.m.
9 a.m. to 1 p.m. in Greddington. Lunch will be provided. Code for Tulsa is working on a criminal justice summit, so they'll be bringing in people from around town to talk about criminal justice topics and how everybody can work together to create great things at the library.
Yes.
Be there.
And so I know there's going to be a lot of sessions that are going to be talking about how we can use data to impact criminal justice policy in the state. And then we're also going to have a hack room where we're going to be working on CourtBot. So if anyone is familiar with CourtBot or has heard us talk about CourtBot, we're going to be doing some coding on it at this event. So if you've wanted to check out the CourtBot code, then come do that. And then if you've seen, John Dungan has basically a collection of Python Jupyter notebooks for analyzing the Oklahoma Supreme Court network data. And he can do some very interesting things and ask about very interesting criminal justice questions that you probably didn't want to know the answers to, but now you can get them. Okay, so that's the 24th, which is Friday, and then August 25th, Celia's coming up to talk about quid pro quod. And you have to stand close enough to this thing that the mic can pick you up.
Okay. Hi. So out of a conversation that I had with small business owners, we talked about the fact that a lot of them can't afford high caliber technology people like you. And so I was talking to Luke about the possibility of having kind of a hack night or an event to support small businesses and then offer you an opportunity to be introduced to small businesses in the area, as well as assist them in getting to the next level as far as the customer interface is concerned. A lot of them are very open to trading goods and services for your know-how, and at least give you the opportunity to think about some ideas about how to make their web presence or their technology a little more robust. It expands your portfolio. You can pitch them projects that you'd like to work on, and in the meantime, come and hang out and learn about some of the neighborhood places. So we're going to kick off this Saturday at 5 o'clock. Lambrusco's over on 41st and Peoria. How many people have been to Lambrusco's or eaten Lambrusco's food? Okay. Is that a good place to start? All right. So definitely she will feed you. It's a 33-year business, and so you get a chance to come and at least experience the store and some of our food, and then you want to dive in and look at our website and talk about how things can be better. We'd love that, any suggestions you come up with. And then I'd love to talk about what other kinds of businesses might appeal to you. Maybe in this crowd, dry cleaning, not so much, but everybody needs, I mean, you know, I don't want to be assumptive, but I'm not going to dry cleaners anytime soon, right? So maybe like oil change, or, you know, anything that you think of where you're going to pay somebody for their goods or services anyway. Well, perhaps they can use some help. So James came up with the name Quid Pro Code. There's a channel in Slack, and come and join us. Join us this Saturday and see how it goes, and then let us know what other kinds of businesses, and we'll just, you know, go to a brew pub or whatever else you think would be interesting. All right, thanks. Yes. Huh? Just show up. Come on down. 5 o'clock on Saturday, and then I'll try to keep posting on the Slack channel that we created for any other things that come up. But I talked to the Brookside Neighborhood Association, and the Business Association is very interested if this becomes something that's interesting to all of you, right? If it's not interesting to all of you, if it's not win-win and it's not fun, we're not going to do it. Is that fair? Okay.
And yes, there is a Quid Pro Code Slack channel now. So if you're on the Techlahoma Slack, you can go look for that one. And I'm sure we'll have all the details there. Okay, Tulsa Lamb to lunch. Where's Darren? Is he here? Is that? Yeah, there he is. Okay. Okay, best name.
All right, so on Tuesday, last Tuesday of the month, 11:30 to 12:30, we're going to talk about a way of reasoning about your applications is a little bit different. We're going to talk about higher kinded types and how you can use those to make your applications more flexible, more reasonable, and easier to test. So if you're interested in functional programming and what all that means, please come next Tuesday.
Okay, also, Tasha K, you want to come up and give the shout out? Or, okay, Dave's going to come up and give the shout.
Hey, I'm sure you guys already know this, but the Maker Faire is this Saturday at near the Expo Center, or whatever it is they're calling it this week. It's from 9 a.m. to 5 p.m. Come and go. They have all kinds of cool electronics and cosplay and model rockets, airplanes, library, 3D printers.
On the way to Lambrusco.
And I'm pretty sure it's still free this year. Come while you still can. Yay.
Okay, and September 11th. Wow, September is already here? What the heck? Okay, so you're going to, Max, you want to come up and talk about the Tulsa UX one?
Hey guys, so on a few Tuesdays from now on September 11th, we're going to have Ryan Husselberg from OU. He is going to give a presentation that's about how the team at Oklahoma University has attacked the multitude of user experience problems for the consumer and how we're slowly closing the gap between feature-rich enterprise products and simplified consumer apps. He's the lead project or product engineer there, and so it's been pretty interesting. He was able to basically they had no UX and no human-centered design stuff at all in any of their like outward-facing products, so any of their websites or anything else, and he's turned that whole thing around and built a whole team. That's going to be pretty awesome. So again, September 11th, right here at 6 p.m. It'll be just like this. Just like this.
Okay, and then finally, where's Nathan? What are you? I'm gonna do. Oh man, you added something. What did you add? Oh yeah, you have to come talk about it now, right? Okay, so yeah, so I'm giving another tech talk at the library. This one's gonna be on machine learning, and that's September 14th, 12 p.m. Though, oh, dang it, that's gonna be like right when you're having a baby, though. Not you, Kat. No, Yaya back there. So, yeah, because I was like, oh, I need to get Yaya on that one too, but okay, this will be tough. It is a happening place. Okay, so now, Nathan, October 10th.
I'm Nathan. How many people have heard of OWASP? It's a pretty good number. Anybody a member of OWASP? Much, much less, approaching zero. Including Luke. So including me, I think there's one. So Luke will be tomorrow. That's the rule. So I'm a former developer turned security guy, consultant, and do all kinds of security things. Luke's a developer, and together we are wanting to form an OWASP chapter. OWASP, several of you have heard of it. If you haven't, it's a international organization. Stands for Open Web Application Security Project. They've actually kind of gone away from just web, and they focus a lot more just on general application security. So the plan is right now, and some of this is still tentative, but October 10th, we've got a room registered here at 36 Degrees North. We're going to do lunchtime from 12 to 1. We're hoping to get some sponsors to be able to provide a good lunch. And basically, we're going to bring in non-vendor speakers to talk about security application stuff, whatever that may be. So we'd love to have everybody join. It's a great opportunity to get out of the office and go have a free lunch. More importantly, the more folks that show up, the easier it'll be to get sponsors to say, hey, we've got a good group here. So we'd love to have you guys register. That's it. If you have any questions, reach out to us. We're both on the Techlahoma Slack. So. One more thing. OWASP looks great on a resume. Just saying.
Okay, so unless somebody added something, I guess I'll refresh just in case everyone's adding stuff. Okay, so we're going to now get into our sessions and subgroups. We have UX App Building 101 group discussion. Max, you want to come pitch about that? Sure. I'm skipping over the Code for Tulsa because I think Duncan and Carlos are not here, so I don't know that we can do that without them. Oh, wait. You're here. So we could do core bot, right?
So tonight's group discussion will be in conjunction with Andrew Jenkins. Raise it high. So he approached me basically asking some questions about how to get an app off the ground at Tulsa UX. And so the group discussion is really going to be more of a kind of war stories and some kind of general knowledge share about getting apps off the ground. I've got kind of his questions categorized into categories and kind of work through those together. It'll be some whiteboarding and stuff, so it'll be a fun. If you've built an app and want to talk about it, this is the breakout session for you.
All right, and then someone added MET recycling app. Who's that? You want to come up and talk about that breakout?
All right, so the Tulsa Met is a nonprofit that is chartered to help with recycling in Tulsa. Recently, I did a design sprint with them, prototyping a recycling app. It's basically around the question of, I have this thing, what do I do with it? A problem we probably all face at some point in time. And since they are a nonprofit, their budget isn't huge. Their board is already a little angry about how much money we've spent, but you know, we're going to win them over with love and hugs. But in the meanwhile, we thought about how we might find aspects of this app that technical needs that would be useful for some other apps. It's using a lot of mapping, for example, and I understand there's somebody who does some mapping, or a wizard who's come in. That's one possible area. Basically, we want to kind of take a look at it, see what could be useful for other projects, and then turn that into like a Code for Tulsa, Code for America style open source project. So we want to do a breakout on that. If you're interested, please come on by.
Okay, so I also had one that I have put together. I didn't update this page, but basically I can give a talk that I get a somewhat more refined polish, thanks to Kat, on a Bitcoin and cryptocurrency talk that I can give. So I'm going to give that one, and I think we'll probably skip the Code for Tulsa one that we had planned because Carlos and Duggan aren't here. So is that fair? Yeah, so they'll do that thing on, yeah. Yep. Yeah, so we'll do that one on Friday. Okay, so just show of hands, just so we know which rooms to break out into. The 3 different talks was UX, App Building 101, the Met Recycling app, or Bitcoin cryptocurrency. So the first one, UX group discussion, 1, 2, 3, 4. Okay, and then Met Recycling app, 1, 2, 3, 4, 5. Okay, and then Bitcoin and cryptocurrency. Just like put Bitcoin in something. And oh man, I want that. Okay, so I guess we'll do Bitcoin and cryptocurrency here, and then Max, do you want which of these rooms? I think we've got all 3 of them. I think we have boardroom. Okay. Jamie, do we have boardroom? Right now? No one's in there? Okay. So we can claim it. So UX will go in the boardroom, and then Brendan, where did you want to do either this room or? Video North. Okay, so Video North right here will be the Met Recycling app, and then we'll do the crypto stuff out here. So grab 5 minutes, grab any food or drinks that's around. So. Good. All right. Is it going through? Can you hear it over the... I just need to talk louder? Okay. Okay, I'm going to get started. So I'm going to talk about Bitcoin and cryptocurrency stuff. So if you don't want to hear about that, or if you're sick of hearing about that, then you can find another room probably. Or you can just put on some big headphones and ignore me. That's fine too. So for anyone who doesn't know me, my name is Luke. I'm a privacy and security engineer for Firefox, and I'm also very involved with Techlahoma. And this talk basically happened because I got a hold of this book called Bitcoin and Cryptocurrency Technologies, and it was exactly what I needed whenever I kept hearing about Bitcoin and cryptocurrency, and I was like, what the heck? Those people are talking about dark magic and wizards, and like it must be some kind of weird stuff. This was like the perfect book that really breaks it down and helps you kind of understand that it takes the magic away. And I always love when things seem magical and then you find out that they're not magical. So this is the book that I would definitely suggest. I have like maybe 200 plus slides, and I can only get through the first chapter and a half of this book, which ends up being like the primitives of it. But the book itself is much easier to sort of ingest than what I'm about to throw at you very quickly. Oh, do we have it at the library yet? No. Oh, okay. Not yet. It's coming, though, soon, though, right? Sure. Yeah. Okay, so one of the things that I always wanted to kind of find out about was where did Bitcoin come from? Like, it seemed like it just happened all of a sudden, and it was huge. So it didn't come out of nowhere, and in the book they say the path to Bitcoin is littered with the corpses of failed attempts. So these are sort of all of these failed digital money cash attempts that are in the history of Bitcoin. The only one that's still around from this list is basically PayPal. So they still exist. So how and why did all of it start? So a little bit of this is just about finance itself. So you have to go from, in the beginning, there was barter, right? But the problem with barter is coordinating everything. So then there were credit ledgers, but credit ledgers have a problem where you could default on your loans or anything like that. So then we had cash, right? And so cash solves a lot of problems. The transaction order doesn't matter like it does in a credit ledger. There's precise values now for things, but there's a problem with cash where how do you actually get a cash system to start up? But the point of all of that is just to say that the pieces of Bitcoin that are complicated because the financial problems that it solves are complicated, right? So it is a bit complicated, but there's a reason that it's complicated. It wasn't just like people kept throwing on NPM modules to make it go better, right? Which is what we do in web development, but the crypto people actually have reasons for what they do. Yeah, left pad. We're all screwed. So those financial problems are both online and offline. Finance online, the thing we're all used to is credit card payments to websites, right? The problem here is that sites get breached, and now there's credit card data sitting in these sites that have been breached. So one mechanism that protects against that is like an intermediary payment provider, like a PayPal. So now you put your credit card in one place, PayPal, and they lock it down very securely, and then they pay other people. So now you haven't put your credit card information all over the internet. You put it in one place, and they're your intermediary. But that gets complicated, so there's a problem with that, where these intermediaries, if you've ever implemented Stripe APIs or PayPal APIs, all that stuff, you've seen this kind of complication. Some of the major ones will simplify that process, but they also charge fees, right? So usually it's 2.9% plus 29 cents, I think, is like the standard fee. So the problems with this online credit system that we have is there's still risks to these transactions, like credit cards can expire and all this stuff, and there's these processing fees. So if we could come up with online cash, we could probably get away from some of those. So there's no defaults on these transactions, and there's direct payments instead of paying these third-party fees. But if you think about physical cash is kind of like a promissory note. So a dollar is actually a promise from the U.S. federal government that says this note is legal tender for all debts, public and private, with love, Treasurer of the United States. So it's like this promissory note. It's not actually a physical valuable thing like gold anymore. And digital cash actually is similar to this. So think of these digital cash things as promissory notes, and that'll get you one step there. But you have to the book says you have to eat your crypto vegetables before you get to eat the Bitcoin pie, right? So there's sort of these crypto primitives that I'm going to talk about in this talk that build up to Bitcoin, and you sort of have to get these things under your belt in order to understand how Bitcoin works without being magic. So here is our Bitcoin food pyramid. So at the bottom, the base, the most fundamental primitives are hash functions and public key cryptography. So I'm going to start out, if you think about cash being a promissory note, and it's just me saying, the bearer of this note may redeem it for $1 by presenting it to me with love from Luke. So there's all kinds of problems with this sort of digital cash item. So there's tampering, forgeries, double spends. So one problem would be tampering. Like if someone were to take $1 and just paste two more zeros onto a $100 bill, right? Like, oh, look at that, it's a $10,000 bill. So if someone's tampering with this note, they say, hey, you can redeem this for $1 million by presenting it to me, love Luke, and then someone could come to me and say, hey, you owe me $1 million. So how do you make this message tamper-proof? And the answer here is the first part of the pyramid, of the crypto pyramid, which is not encryption. So this part is the cryptographic hash functions. So this is the first thing I'm going to talk about down here. Everything is really built on top of them. So I'm spending a lot of time on these because they're kind of the base of a lot of cryptocurrency. Bitcoin happens because cryptographic hash functions are at the bottom of it. So in general, a hash function takes an input message of any size and produces some fixed size output. And one of the big rules is it can do this really fast, even on really big inputs. So for example, if your message is we the people of the United States, yada, 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 and you run that through a hash function, it's going to come up with some 60-character string. I'm going to shorten that to 6 characters here, just because it's easier to present that way. So you've got some message, and when you run it through a hash function, you get a very small string that represents that message. If you take a different message, like the bearer of this note may redeem it, you'll come up with a different hash, right? So a different message gives you a different hash. So if you want to use cryptographic hash functions, you need a few more things besides just the ability to turn a message into a small digest. So the first thing you need to do is you need to resist collisions. So this means that 2 different messages should never produce the same hash, right? So if you have 2 different messages and you run them through the hash function, they should never come up to the same hash digest. This is a hash collision, right? So that's the first property that a cryptographic hash function has to have. The other one is called hiding. So if you're given the hash value, it's not feasible to find the original message. So it should be what's called a one-way function, right? So you're given the hash at the top, you can't get back to what was this original message, right? There's an interesting wrinkle here. So if you have a message space that only has 2 messages, heads and tails, and you hash each of them, and they're different hashes, but it would be pretty easy to find out which one is which. So if you're given the 3E536A, you would go, oh, well, there was only 2 of these, so it's definitely heads, right? So as an aside, which we can talk about later, this is why you shouldn't reuse your passwords. And also, since this is a web developer talk, this is why you have to salt when you hash passwords going into your database. For the love of everything, please be doing that if you're not already. So what you can do is, like I said, if you're web devs and you're used to salting before you put hashes into a database, then this should be familiar with you. You're basically adding a random value called a nonce to the value, and that will make the hash come up with something different. depending on the nonce. So if you just have heads and tails, they come out to those values. But if you were to append an A character, then you get new hash values. If you append B character, then you get even more new hash values. So if you add nonces, if you add random data to your message, then your hash function is going to give you different outputs, right? So then if you're given the hash and the nonce, or if you're given the hash, it's not feasible to find the message or the nonce, right? So that one-way function thing again. The last thing is called puzzle friendliness, which is really, really complicated. The way that I kind of think of it is if you choose a suitably random nonce, it's hard to find different combinations of messages and nonces that come up with the same value. So it's kind of like the collision thing, but there's like some twists that make this a little bit different. Okay, so all of that is cryptographic hash functions, but where do you actually get these things? Well, the good news is decades of cryptographers have been working on this, and they've built it into open source tools like OpenSSL. So if you're on a Linux machine or a Mac machine, and I think even Windows now has OpenSSL command line, especially with probably PowerShell, you can just echo some message and you can pipe it to OpenSSL SHA-256 and you'll get a hash, right? So you can just start creating these hashes of these messages. You could even do this with not just messages, but with data files, right? And so I'm very confident right now that SHA-256 is one way because I'm showing you the contents of my Etsy hosts and my Etsy password, and Nathan is freaking out back there. Oh, he's not freaking out. Okay. Yeah, not SHA-1. So SHA-256 stands for Secure Hash Algorithm with 256-bit digests. So it is just a cryptographic hashing function that has been out there for a while, and SHA-256 is actually what Bitcoin uses, right? So SHA-256 is used in Bitcoin, and it's basically been established over decades that this is a cryptographically safe hash function until, somebody else goes and breaks it, and there'll be another shappening, and half of all of your servers will go down. So then the next thing you need after the hash functions is you need what's called hash pointers. So this is one thing up. When you've got your hash functions, a hash pointer is you have your message or your data, and you hash that. You've got the hash value. A hash pointer is the hash of that and pointing at the original data that generated the hash, right? So the hash pointer is where the full plain text data is stored and a cryptographic hash of that data, right? So it's a bit of a nebulous concept. It's actually easier to understand when it's used in a blockchain. But hash pointers enable everyone else to verify the truth of the data. So remember that we said that if you're given the hash value, you can't go back to the message. But what a hash pointer does is says, here's the original message and the hash value. Yeah, so you have the original message, you can hash it yourself, and you can verify that, yes, this is the hash for this message, right? So that's what the hash pointer gives you. Now, the hashes give us confidentiality, which is that one-way thing of them, right? So you could hide things with a hash. That's why you can hide passwords with a hash, and it's confidential to whoever entered the password into that hash function, right? That will keep something secret. But now these hash pointers are dropping that confidentiality. What they're instead giving us is the integrity, right? So if you have a hash pointer to something, you can be sure that no one manipulated the original message because you can check the hash that they claim generated the original message. Is that making sense? So the hash pointers and the hashing is not there to keep things secret. It's there to keep the integrity, so you know that they haven't been tampered with, right?
If it has been tampered with, then you can prove
Yes, you can see that it has been tampered with, right? Okay, so there's a lot of people are like, oh, where does the encryption come in? Like, spoiler alert, there's no encryption. Okay, so now you need a blockchain. If you've got hash pointers, the next thing you can build on top of that is a blockchain. So a blockchain is a linked list with hash pointers. So each of these blocks at the very top is a hash pointer to the previous block of data, right? And its hash. So the first block here is pointing to whatever the previous block was, which was all of its data, and then hash that previous block, and then that's what I'm pointing to. So you can verify. I say that this is the original data, this is the hash, and you say, yes, you are building on top of the proper data, right? So every block in a blockchain points to the previous block, and the hash can make it so that you can verify that the entire chain is true. So now you have this tamper-evident log. So if somebody were to ever try to publish a new version of the blockchain and tamper some data out here in this block, you can catch it anywhere downstream from that block. Does that make sense? I'm losing people. All right, so I can tell I'm losing people, but stick with me. It's gonna get better, hopefully. If it doesn't, there's more pizza. Is there more pizza? Yeah. Okay, there's more pizza. So further down the line, if someone has messed with the data, then you can actually check and verify and see that someone's messed with the data. So now we can have this like tamper-proof ledger of digital dollars where one of them says the bearer of this note can can redeem it for $1 by presenting it to me, and then the next dollar can say the same thing, and I'm building on top of the previous dollar. So that dollar could be spent a couple of times, and everyone knows that it's basically being spent in a chain, right? So now if a forger comes along and I have my computer and I've sent this dollar and some forger gets a hold of this dollar, they could still go make a bunch of copies of this, right? So even though it's cryptographically sound, they could say like, oh, I've got a bunch of copies of the last dollar on the blockchain. Here you go, here you go, here you go, here you go, right? So the forgery solution is to get unforgeable signatures is digital signatures. So to have digital signatures, you have to have public key cryptography first. So if we look at the public key cryptography, how many people are familiar with public key crypto? Okay, so a good amount of the room, which is good because I'm not sure if these videos are going to work. But if you're not familiar with it, Khan Academy has a Journey into Cryptography course that has a section in it called Modern Cryptography. And if you've ever wondered about how in the world is all this modern crypto going on, this section is amazing. There's a cool sequence of 8 or 9 videos. They're all 5 minutes or less. But this was the thing that really made it click for me when I oh, well, I know there's these things called public keys and private keys, but I don't really know what the heck, where they're coming from and what kind of magic are they doing. What? What? Ah. Ah, it's echoing. Are you fixing the echo? Hello? Good? Better? Okay. I'm just going to sound very authoritative, like I'm being repeated all the time. The room got suddenly bigger. Yeah. Okay, so I'm going to try this video. If maybe this video will work. Let's see. Maybe this video won't work at all. Nope.
Computers, they always do exactly the same thing every time.
Play the thing. Ah. How do I make it play? Come on, Keynote. Work your scientific nonsense. Can you just pull it up in the browser? Yeah, I'm going to try that next. Okay. So let's do... So this is the section that I was talking about, modern crypto. Let's see if this works.
Practice.
Oh, my audio is not going through. I think I can fix that.
Up until the 1970s, cryptography had been based on symmetric keys. That is, the sender encrypts their message using a specific key, and the receiver decrypts using an identical key. As you may recall, encryption is a mapping from some message using a specific key to a ciphertext message. To decrypt a ciphertext, you use the same key to reverse the mapping. So, for Alice and Bob to communicate securely, they must first share identical keys. However, establishing a shared key is often impossible if Alice and Bob can't physically meet, or requires extra communications overhead when using the Diffie-Hellman key exchange. Plus, if Alice needs to communicate with multiple people, perhaps she's a bank, then she's going to have to exchange distinct keys with each person. Now she'll have to manage all of these keys and send thousands of messages just to establish them. Could there be a simpler way? In 1970, James Ellis, a British engineer and mathematician, was working on an idea for non-secret encryption. It's based on a simple yet clever concept. Lock and unlock are inverse operations. Alice could buy a lock, keep the key, and send the open lock to Bob. Bob then locks his message and sends it back to Alice. No keys are exchanged. This means she could publish the lock widely and let anyone in the world use it to send her a message. And she now only needs to keep track of a single key. Ellis never arrived at a mathematical solution, though he had an intuitive sense of how it should work. The idea is based on splitting a key into two parts, an encryption key and a decryption key. The decryption key performs the inverse or undo operation which was applied by the encryption key. To see how inverse keys could work, let's do a simplified example with colors. How could Bob send Alice a specific color without Eve, who is always listening, intercepting it? The inverse of some color is called a complementary color, which when added to it produces white, undoing the effect of the first color. In this example, we assume that mixing colors is a one-way function because it's fast to mix colors and output a third, and it's much slower to undo. Alice first generates her private key by randomly selecting a color, say red. Next, assume Alice uses a secret color machine to find the exact complement of her red, and nobody else has access to this. This results in cyan, which she sends to Bob as her public key. Let's say Bob wants to send a secret yellow to Alice. He mixes this with her public color and sends the resulting mixture back to Alice. Now, Alice adds her private color to Bob's mixture. This undoes the effect of her public color, leaving her with Bob's secret color. Notice Eve has no easy way to find Bob's yellow since she needs Alice's private red to do so. This is how it should work. However, a mathematical solution was needed to make this work in practice.
Okay. Oh, but does it start to play now? What a joke. Okay. So here's the math, which is like 5 more videos, and if you're into this stuff, they're very cool videos. But basically, the 3 main concepts: the phi function is hard to calculate, except for prime numbers. Multiplying large prime numbers is hard to reverse, which is called the prime factorization problem. And numbers can be hidden with modular exponentiation. So there's like a bunch of videos that explain how you go from like Euclid to Euler to prove that all of that is true. We're not going to do that. So hopefully this video will work.
Let's do a simple example to see all of this in action. Say Bob has a message he converted into a number using a padding scheme. Let's call this M. Then Alice generates her public and private key as follows. First, she generates 2 random prime numbers of similar size and multiplies them to get n, 3,127. Then she calculates phi of n easily since she knows the factorization of n, which turns out to 3,016. Next, she picks some small public exponent e, with the condition that it must be an odd number that does not share a factor with phi n. In this case, she picks e equals 3. Finally, she finds the value of her private exponent d, which in this case is 2 times phi of n plus 1 divided by 3, or 2011. Now, she hides everything except the value of n and e, because n and e make up her public key. Think of it as an open lock. She sends this to Bob to lock his message with. Bob locks his message by calculating m to the power of e mod n. Call this C, his encrypted message, which he sends back to Alice. Finally, Alice decrypts his message using her private key, D, accessed through her trapdoor. C to the power of D mod n equals Bob's original message M. Notice that Eve, or anyone else with C, N, and E, can only find the exponent D if they can calculate phi n, which requires that they know the prime factorization of n. If n is large enough, Alice can be sure that this will take hundreds of years even with the most powerful network of computers. This trick was immediately classified after its publication. However, it was independently rediscovered in 1977 by Ron Rivest, Adi Shamir, and Len Edelman, which is why it's now known as RSA encryption. RSA is the most widely used public key algorithm in the world, and the most copied software in history. Every internet user on Earth is using RSA, or some variant of it, whether they realize it or not. Its strength relies on the hardness of prime factorization, which is a result of deep questions about the distribution of prime numbers, a question which has remained unsolved for thousands of years.
So, anyway, that's the public key crypto. All of that is basically, there is very, very, very convincing math that yes, you can split a key into two pieces and have a public key and a private key. So, if you have public keys and private keys, now you can do digital signatures. So digital signatures, what you need from these is that only you can sign your signature, but anyone can verify that it's valid. And the signature is attached to, can only be attached to a single document. So it can't be used to indicate that you agree to some other document. So this is not encrypt and decrypt, though it does use public keys and private keys like that. It's sign and verify. So to do this, you need basically two functions. One's called sign, that takes the secret key and a message, and one's called verify. It takes the corresponding public key, the message, and the signature. So that's what I just said, and let's say that you have the message is your dollar, and you have the signature that I signed it, and then the public key can verify that yes, it really was Luke who signed it. So these also come from decades of cryptography built into OpenSSL. If you've ever used OpenSSL, you can generate key pairs like a public key and a private key. You'll have a secret key and a public key file on your machine. Then you can start signing messages or signing data with your secret key. This is how you sign it. So OpenSSL, sign with this secret key, this message, and output it here. And then if you want to verify it, OpenSSL, digest verify, public key, signature, Luke dollar signed, and yes, that's valid. It was definitely signed by Luke's private key. So now the forger, if they're trying to sign something, they don't have my secret key, so they're going to have some other secret key, and whenever someone tries to verify it, it's going to fail, right? So that's going to come up invalid. So now you have these unforgeable digital signatures, okay? So now we finally have enough to build a really bad cryptocurrency. So we're up to here, and the one in the book that they build out of all of this is called Goofy Coin. So the rules of Goofy Coin are as follows. Some designated entity named Goofy can create new coins anytime they want to, and the coins belong to Goofy. And whoever owns a coin can transfer it to someone else. So first, Goofy creates these coins. Maybe there's generate a unique coin ID, and then you make this message called create coin, this ID, and I sign that message. Goofy signs that message with their secret key. Then if Goofy wants to transfer some coins to Alice, there's a new message called pay this coin to Alice. And And later, it'll be important that that is actually her public key address. But for right now, Goofy just says, okay, pay this coin that I just made to Alice and signs it with Goofy's secret key. So you know from the original transaction, this coin belonged to Goofy. And then there's another message that says, this coin needs to go to Alice, and it has to be Goofy who says that, right? So then Alice could go on and transfer that coin to Bob. So she says, pay that same coin ID to Bob, and she signs it with her secret key. So in a blockchain, in a cryptocurrency, this looks like the very first block is create coin with an ID, and then the next block just has the pay coin 1, 2, 3, 4, 5 to Alice, and then it points back to the previous block that it's building on along with a hash of the previous block. So you can say, yep, that's actually the right statement, and yes, it includes Alice's signature, right? And then Alice goes on to pay coin 1, 2, 3, 4, 5 to Bob. Okay? Making sense? Okay. Some heads nodding. A lot of the same heads that said yes to public key cryptography. Okay, so in Goofy Coin, you've got Goofy can create these new coins, and whoever owns a coin can transfer it, and anyone can verify the coin ownership by following the blockchain all the way back to Goofy's first coin, right? So there's a security problem here, which is the double spend attack. So this is a lot of blockchain and cryptocurrency stuff has to deal with double spends. So what happens here is that Alice can pay a coin to Bob and then propose a new block that just says, oh, and also pay coin 1, 2, 3, 4, 5 to Chuck, right? So how do we decide which of those ledgers, which of these versions is actually the truth? Which of those coins? Bob or Chuck, right? Yeah, whoever's angrier. So the book comes up with another coin that solves this problem called Scrooge Coin. So Scrooge Coin is basically Goofy Coin, but there's now a designated entity, a new entity named Scrooge, who publishes the canonical public ledger of all the transactions that have ever happened. So when anybody wants to make a transaction, they have to broadcast it to Scrooge, and Scrooge accepts all of the transactions, and at some point bunches them all up into a block, and then signs it, right? And Scrooge can go through and verify that, yes, all these transactions are valid, and it hasn't been double spent, right? So in Scrooge Coin, Scrooge builds a blockchain that Scrooge is going to digitally sign. Each block has a transaction in it with an ID and some contents, and then the hash pointer to the previous block. Scrooge signs the final hash pointer, and then Scrooge publishes the signature and the entire blockchain, right? So again, we have create coins and we have pay coins, but now they look kind of like this. So create coins, and this transaction ID is 1. So coin number 1, there's 3.2 of them, they're going to Scrooge. Coin number 2, there's 1.4 going to Goofy. And coin number 3, there's 7.1 going to Alice. So then when you're going to pay a coin, you have to reference the previous transaction and the previous coin that you're spending when you're going to pay this coin. So in this case, Alice is going to go back to the previous transaction that gave 7.1 coins to her, and she's going to give 1 coin to Bob and then 6.1 back to herself. So she's giving 1 coin to Bob and saying the other 6.1, that goes to me still, right? So Scrooge signs off on all of this stuff. Now if Alice tries to double spend, then she tries to respend a coin from block 1 after Scrooge has already signed block 2, then Scrooge catches her, right? So now Alice has to propose this new transaction that is pointing to a transaction in 2 blocks ago using those coins, and Scrooge says, nope, I've already signed that the canonical truth is that you paid that coin to Bob, you don't get to pay it to Chuck, right? So now Scrooge is the one who catches that double spend. So then how does Scrooge know that someone can pay a coin? So when Scrooge signs off on everything, like what stops Bob from submitting a block that just says, oh, Alice paid me this thing, right? And this is where the public keys as the identities come in, is that the sender, so again, the sender signs a message. Now that message has a signature attached to it, and the receiver that has a public key can verify it really was that person who said it, right? So if you equate like these public keys are basically the sender, and then the private key is just showing that someone can make a provable statement by this person. So just consider the blue key is now a person, right? The public key is a person, and the private key proves statements that are made by that person. So in cryptocurrencies, those are called addresses, and that means that these transactions, what they actually look like is when you're paying Scrooge, you're actually paying Scrooge's public key, right? When you're paying Goofy, you're paying Goofy's public key. So now in the transaction, Alice's public key address is the one that received the coins, so only she can sign transactions to pay the coins to someone else. So the coins were paid to Alice's public key, and there's a new message, a new basic claim made that is paying these coins to 1 to Bob, 6.1 to Alice, and so that has to have Alice's signature on it, right? And so Scrooge can verify that, yes, that is Alice's signature on that, and yes, in the previous block, she had those coins, and yes, it's not being spent somewhere else, right? So Scrooge can detect if Bob is going to try to make this transaction with their own signature and can reject that. So again, all that same stuff. So now in Scrooge Coin, we have public keys are the addresses that are receiving coins. The private keys are signing transactions to send the coins. Everyone, including Scrooge, can verify all of these transactions, which prevents the fraudulent spending and the double spending. And then Scrooge is the one who signs the canonical ledger of transactions that have happened in the blockchain. Okay? So Scrooge is the one maintaining the ledger and all the transactions and creating new coins. So what could possibly go wrong with that, right? So then, of course, how do you get rid of Scrooge? So Scrooge is the centralized thing that you want to get rid of. Without Scrooge, who is going to maintain the ledger of the transactions? Who's going to decide which transactions are valid? And who's going to create new coins? And so now we get to coin miners, right? So in most cryptocurrencies, I think, all the ones I can remember reading about, coin miners are basically the ones maintaining the ledger. They have authority over which transactions are valid, and they're creating new coins. So who are coin miners? Well, if you look at Bitcoin specifically, Bitcoin is a peer-to-peer network. So it's like Tor, where you can participate, you can download Bitcoin. If you go to bitcoin.org, you can download Bitcoin Core. It will run a little, it'll run a little client on your machine that will then connect to the rest of all of the Bitcoin clients, all the Bitcoin nodes that are out there in the world. Note, if you download this and you run what's called a full node, it will use up all your disk space because the ledger at this point is 144 gigabytes when I downloaded it, and I had to delete a whole bunch of my video games, which screw that. So, I did it to run some data analysis on the ledger, and that was kind of fun. But then I was like, okay, this is eating up 150 gigs on my hard drive. I don't want that. Yeah, and it'll eat up a lot of bandwidth too, especially if you're running a node that does all the validations. So in order to pay Bob in Bitcoin or most of the other cryptocurrencies, Alice broadcasts the transaction to all of the other Bitcoin nodes. So Alice has this transaction. She's going to sign it with her private key and then just broadcast it to the network. So she's running a node, and she puts this new transaction in there, and that node, she says, basically send that out to all the other nodes that you can find. And then these Bitcoin nodes are governed by what's called the distributed consensus protocol. And here I'm going to be going covering this stuff way too fast because we're already at 7:18 and there's just way too much to cover. So a lot of this stuff I'm not going to go into the primitives of exactly how the distributed consensus protocol works. What's that?
If you're not going to get to the thing, I want to know one thing. This is a thing I've never understood. How do you prevent race conditions if you have everything distributed?
Oh, okay. So I'll get there. Yeah, I may be answering that towards the end. So in the Bitcoin consensus protocol, new transactions are broadcast everywhere. All of the nodes will basically collect all the new transactions that they've heard about and turn that into a block. So here's a block full of transactions. And then in each round, a random node gets to add its block to the end of the blockchain, and the other nodes accept that block only if all the transactions in it are valid. So remember, everything in there has to be validly signed by the people who own the coins, right? And anyone can validate that. The node who proposes the block, and then all the other nodes who see, oh, this node is saying that this is the next block. Well, I'm going to go through and make sure they actually did all their hashing right, and yes, it is valid. And so the other nodes can be like, yes, you made a good block, so we're going to accept that. So there's this implicit consensus that goes on over time. So you have multiple rounds, and in each round, some random node is selected to make that next block. So now you have to think about what if the random node is malicious, right? So now let's go to Alice running a malicious node. What could she do? Could she steal Bitcoins? Well, no, because even in her block that she gets to put on the blockchain, she can't forge Bob's signature on the coins that belong to him. So if she tries to propose that as the next block, the other nodes say, nope, that's not the next block. We go to the next node, they get to do the next block. So what about like denying Bob the ability to participate? Not really, because even if she refuses to include Bob's transactions in the blocks that she makes, the next node can basically just include it anyway, right? Now, then you get to the same kind of problem you get with Tor if someone's running 50% of the 51% attack, right? Yeah. So 51% attack is a thing in Bitcoin just like it's a thing in Tor. And there's a whole section of the book on that. But how about double spends? Well, this one gets a little bit interesting. So let's say that Alice buys a blender from Bob and pays him in Bitcoin on block number 123. And then by chance, Alice gets to make block number 124, right? So now Alice gets to make block 124, and she's going to pay Chuck with the same coins that she just used to pay Bob. Whoa. So which block will the next node extend? Because both of these are valid, right? So the next node could see either one of these blocks. She could broadcast both blocks and just see which nodes pick it up, right? And the general rule is that nodes will usually extend the block that they first detect on the network, so it could be the double spend block, right? So in this case, the next node picks up on the spend to Chuck and builds a block on top of that. And then nodes tend to extend the longest blockchain, so the next node would keep going, and Bob's coin is now orphaned. So it's on a branch, and it can't be spent. So if you do this, then yes, Alice could potentially double spend, right? So the trick here is Bob should really just wait until he knows that his coins are in the longest blockchain before handing the blender over to Alice, right? This is literally how it should be done. Now, in Bitcoin, waiting for 6 blocks is basically the common heuristic, right? So it's basically if your coins are in the last 6 blocks ago, then you can just go ahead and start spending those now, right? So you won't be able to spend them until you wait for about 6 blocks to be made that included the transaction of the coins you're wanting to spend. It's just a general rule of thumb, which takes about an hour on the Bitcoin network. And I'm not going to get into Lightning and all the other, Buddy can tell you about Lightning and all that stuff. Okay, so in Bitcoin, the security here is that the invalid transactions are protected by crypto, by those digital signatures. And that's enforced by the consensus of a majority of honest nodes building blocks only on valid transactions. The double spends are protected by the same consensus and just sort of waiting enough time to see that a transaction is in the longest chain. So how are we going to make the majority of nodes behave honestly, right? So yeah, not crypto, incentives. And I love this line from the book that was basically, okay, Bitcoin actually ends up working better in practice than in theory. Like if you just like look at cryptocurrencies and Bitcoin and you write it all out, you're like, that is the stupidest thing. No one is ever going to treat that the right way. Like, just by the technology and the crypto in it, yes, it's completely open to abuses. But the sort of like twist here is that Bitcoin is also a currency, so you have incentives, right? So you have this consensus over time, and you have these incentives. So can we give nodes an incentive to behave honestly? Well, there's no real identities, so we can't exactly mail them cash. If only there were a digital currency we could give them without having to know their real identities. So you can see where this is going. What happens is what's called a block reward. So this is, in each block, there is allowed to be one create coins transaction, right? So it's the top transaction in the block. So Alice, when she's creating a block, she mines a block, and she gets to create new coins that are paid to herself, right? So the first transaction in a block is going to be transaction number 0, and the value is 25 coins that are being sent to Alice, because Alice is running the node that is actually creating this block, right? So there's a financial incentive to be honest, because miners will only include valid transactions, and because they want their own create coin transaction to be included in the long-term consensus block, right? So they want their create coins transaction to be included 6 blocks from now, so that they can start spending it, right? So that incentivizes them to keep the valid blockchain going, right? Okay, so back to this distributed consensus protocol. The new transactions are broadcast to all the nodes. Each node collects a new transaction into a block. In each round, a random node adds its block to the end of the blockchain. So how do we pick a random node? And the answer here is proof of work. So proof of work is we're going to approximate randomly selecting a node in proportion to some scarce resource, right? And in Bitcoin, it's computing power. So nodes compete with each other on computing power in order to win like the ability to create the next block on the blockchain, right? And this is where we get to that puzzle friendliness part of hashes. So back to the puzzle friendliness, if you choose a suitably random nonce, it's hard to find a different message and nonce combo that will come up to the same value. So hash puzzles in Bitcoin mining basically work like this. If you create a block, a node is required to find a nonce value such that when you combine that nonce, the previous block's hash, and a list of a bunch of transactions, valid transactions that are out there, then the hash output has to be a string that falls into some certain range, right? So the hash of the nonce, previous hash, and all the transactions, you're going to try and make that hash end up in some kind of target range. So in Bitcoin, the target is literally a string that starts with some number of zeros, right? So if you SHA-256 a whole bunch of strings, it's going to come out with a bunch of nonces, and you change the nonces all the time, then you're going to come up with a bunch of different strings. And in Bitcoin, it says basically you have to keep hashing that with new nonces until you find one that starts with 8 zeros. You find one that starts with 8 zeros, you did it. Good job. So this is just me on my terminal. Let's see. Where's my mouse? Oh, here we go. Oh, not working. Okay. So basically, I'm just echoing a string, and it's the same string, but I'm using a different nonce each time, a random like hex, 10-character hex thing. And you'll notice that like every time I run that hash with a different nonce, it's coming up with a different value, right? So miners are basically taking the hash of the previous block in the blockchain, all of the valid transactions that they've heard about, including a create coins transaction to themselves, and then some nonce value, and they're just hashing that and seeing if they get a bunch of zeros in the front. And if they don't, they pick a new nonce value and they just keep going. And they go and they go and they go until they get one that has all the zeros that they want. Whoa. Okay, so just to show you that this is actually true, we're going to go to this site, blockchain.com. Wait a minute. Is this the right one? Blockchain.info? Yeah, I think this is it. Okay, so blockchain.info will basically show you the current state of the Bitcoin blockchain. So the height is there are 537,720 blocks in the Bitcoin blockchain. The last one was found 15 minutes ago. There were 106 transactions in it. It included 459 Bitcoin worth of transactions being paid. We don't know who actually related. I'm sure you could find that out somehow. It has the size. If you click on the block, you'll see that over here, the hash itself is, like I said, with all those zeros in it. Probably can't see it right there. Where'd all those zeros? So there's the actual like hashes is 0, some number, right? And then I think anyone else familiar with this? Do you know if it'll show you the nonce? Yeah, it was down there. Scroll down. Just right above the hashes. Oh, yeah. There it is. There's the nonce that they used. Right there. So just some number. Yep. It's just that simple, y'all. Just keep trying a bunch of numbers. So that's basically what's going on. And here's all the transactions, right? So this one, there's no inputs. This is the create coin transaction. And it's being paid to this address. So whoever owns this owns the miner that created this, most likely, right? And right now, the block reward in Bitcoin is 12.5 Bitcoin. It just changed to 12.5 recently. How long ago did it change? it basically is halving every 18 months. I think it halves every 18 months. There's a finite amount of Bitcoin that will ever be produced in the world, and I think it's 20 million Bitcoin total. 20 or 21 million Bitcoin will.
So the reward is going down as the problem becomes harder?
So yeah, so we'll move that to questions where Buddy can also help us answer those questions, because there are answers to the questions, but I wanted to show one more thing because, oh yeah, the web. Okay, so we're out at Tulsa Web Devs, so I wanted to throw something in at the end of this. Was like, oh crap, what does that have to do with the web? So who's heard of cryptojacking? Just a few of us? Okay, so this is cool. So even people who maybe are into crypto and web, this may be the first time that you've seen it. Yeah. Yeah, okay. So cryptojacking, if you want to cryptojack, you can just include the script source equals coinhive.com/lib/coinhive.min.js on your page, and all the visitors to your site will be off to the races trying to mine cryptocurrencies, right? So here's actually the JavaScript itself. It's just a huge minified JavaScript file. I took it through a deminifier and looked at it. What it's basically doing, it's creating a web worker with a number of threads that's equal to the number of CPU cores that are available, up to a maximum of 8. So it's going to grab every single core on your machine. Then it loads a WebAssembly program that I'm sure is a mining. I'm sure it's mining that has been written in C or something really, really fast, and then compiled down into WebAssembly. And it's loading that into the worker. And I love that, when I was looking at the code, it's oh, it has a throttle parameter. I'm like, oh, that's nice. And then the throttle, it's set to use 99% of your computing power. That's the default throttle. Oh, look, they're throttling. That's really nice. They left you 1% of your CPU to try and use the web with. Oh, good job. Nice. Super stand-up tech bros. Okay, so then what it also does is it creates this WebSocket connection between your browser and their server, so that their server can basically notify the program that's running if a new block has been found. So it sends a new block down to the worker on the client. And it also, in some cases, if the server node hears about new transactions, it will send new transactions down. It doesn't necessarily have to do that. And we can have more questions about how many transactions does a miner want to include in their block and all that. There's a lot of math that tells you can calculate exactly how many transactions you should be aiming for. And the server notifies the browser. So that's basically cryptojacking. Let me see if I have that script still up somewhere. Not there. Oh, here it is. Okay. Let me put this over here. So here's basically start to finish. Create a new thing called a miner and have all these parameters. Yep. Yeah, where's the throttle 99? Did you see it somewhere? Yeah, right at the top there, right there. Yeah, all right. There it is. Yeah, nice crypto miner is nice. So this is where we get into, let me see if I have any more slides. No, these are all old slides. These are all the credits for the pictures that I took from the Noun project. Not that I found one that would tap into the GPU. For Bitcoin specifically, is Monero ASICs resistant? It is. So only certain cryptocurrencies would benefit from having GPU, basically. A lot of the cryptocurrencies that, like Bitcoin and others that are CPU bound and not memory bound, or like proof of stake bound or anything like that, they basically, the mining for them has so far surpassed GPUs that it's not even, don't even try. So that's why these miners basically do Monero and other cryptocurrencies that use a hash algorithm that also requires like some hefty amount of memory or something that's not just CPU, right? Because all of the coins that use just CPU are basically taken over by, mining data centers that are running Yeah. So I think actually Litecoin is basically Bitcoin, but which hash function does it use instead of? So Litecoin uses a different hash function than SHA-256. The word superfish is coming to mind, but it's not that one, I don't think. But anyway, they used a hashing algorithm that basically requires, what is it? Blowfish? Yeah, I think that's it. I think that is it, Blowfish. Yes. But no one here can correct me, so I just made it up. So in any case, some of those hashing algorithms basically need more memory than just CPU. And so that basically is a way where you can't just build an integrated circuit to just do this thing all the time. You would actually have to build something like a motherboard. And then if it requires that, you're what they call ASICs resistant. So there's cryptocurrencies that are ASICs resistant, and those ones you could still do with like GPUs, or they would still benefit from GPU mining. Okay, that's all I have. So I take all the questions or whatever, but.
So the answer to my question of race conditions is delay and consensus, basically?
Yeah, it's the consensus over time is essentially what it is. And there can definitely still be issues. Oh, sorry, the question was, what about race conditions with nodes proposing blocks? And that was the double spend thing where, yes, if you really want to be sure, you just wait a period of time until the sixth block includes the transactions that you're spending. Yeah, it's actually an interesting note that they make in the book comparing it to database consensus, because where database engines typically fight the latency of consistency, Bitcoin basically embraces it and says we're going to make this part of our consensus protocol. Is going to be there's a built-in timer, like blocks should typically arrive every 10 minutes, which means it's typically going to take an hour before you know that you could spend coins that you received.
Do you know about hierarchical wallets?
Yes, it's in the book. So I know a little bit about them, but you have to come up, if you're going to come up and talk about it, you should come here and talk about it. Yeah, no, yes, you should be doing this, cold wallets and hot wallets.
Yeah, so there's multiple types of wallets. He was mentioned cold wallets, hot wallets. Cold wallets are like cold storage to kind of get it out from anyone being able to easily access your Bitcoin. There's hot wallets, which is something like a program called Jax that someone else is hosting a node and you're just kind of interfacing it over an API. They're still fairly secure. They recommend not putting much money in those. That's kind of like your wallet that you carry around in your back pocket. Exactly. And then your cold storage is like your savings account or checking account. But the one thing I wanted to mention for personal security is the hierarchical wallets. They're super interesting cryptography going on there, very complex. But if you've heard of Bitcoin is not anonymous, it's pseudo-anonymous. Since you can inspect the ledger, you can actually, if you can tie your wallet address to somebody, then you can say, hey, everything that was sent from all these people, I can know who's sending what. So there's hierarchical deterministic wallets, BIP44, if you're interested in really diving in on it. But basically, they create a one-time use address. So if you get a wallet, make sure that every time somebody sends you money, that when you go to get a new address, you get a new wallet address, so that you're always getting fresh money to a new address. And it all goes down to called an XPub address, that is kind of the base address that you derive your others that you send out to people. Not a lot of people will make sure that their wallets are refreshing with fresh things. Anyway, so I just wanted to mention that in case y'all get it, just so that you stay safe.
I think I can show it.
Nested wallet, is that more so just so when new transactions come in, there's only that attack surface to be hit, or is that?
Yeah, I mean, yeah, some of it, sort of. It's more to keep your privacy. Oh, sorry.
Sorry, repeat the question and the.
You're basically asking is, do you generate a new one to reduce your attack surface? So is that?
Yeah.
Okay, yeah. So you generate a new one. Sort of, yeah. It's super complicated to try to get it. But it's more for anonymity. It's a pseudo anonymity thing. Okay. Huh?
I can show kind of an example. Yeah. So I can show kind of an example of this, which in a few months, hopefully this talk will include some Hack the Nazis slides, because apparently that's my new theme of talks. So this is the way, if you're going to take like Bitcoin on your site. So this is WikiLeaks, and this is if you want to donate by Bitcoin. What you do is you put this donate to this Bitcoin wallet address on your site. But if I refresh this page, every time I refresh, or I can refresh, I forget how often it takes. Yep. So basically it will generate new wallet addresses for you to give them money, right? So they're generating key pairs. They've got a private key that can spend the coins that are sent to this address, but they're getting new ones all the time, right?
So it's less about the attack service than, okay, I know wallet A sent me a Bitcoin. I can't go see all the other places wallet A sent a Bitcoin to.
Correct.
Okay.
Not unless you have that expo.
Okay.
So let me, hold on. Hopefully this will be worth it if it's still in my, okay.
And has it risen in the audience?
Oh, yes, okay, yes.
So you mentioned that somebody gets an incentive for every block that they unleash, but the incentive is halving. Is there another incentive that miners get?
Yes, so in Bitcoin, there are also transaction fees that the miners, so the question was, we mentioned that there's a block reward, which is the reward that miners get for creating the next block. And then the question is, what happens when there's no more Bitcoins to be made? How are the miners going to keep getting paid for their trouble? And the answer is there's also the concept of transaction fees. So on the transactions, or I think it's, right? Yeah, it's going to be 2.9% plus 30 cents, right? So, but basically, yeah, it's turning into, at some point, the transaction fees will be the things that take over.
So in that case, does Bitcoin have like a slide trajectory? At one point there's a maximum Bitcoin and then eventually it goes all the way back down to zero due to transaction fees? Or asymptotically towards zero?
Yeah, I don't know. Okay.
How are the transaction fees determined?
I think the transaction fees in Bitcoin are proposed by the miner. Aren't they? Or no? Blix is correcting me.
So transaction fees are actually determined by the person sending them. They're usually built into whatever wallet you're using. And miners can choose to reject transactions that have too low of a fee, which is what encourages the fee.
And you can raise it higher to get it.
So if they don't accept your transaction, all right, I'll give you a little bit more.
Yeah, so when you do a 2,000 Bitcoin transaction, you're jacking that fee up because you want that thing done fast.
Now I don't know if you can change the fee once you've sent the transaction.
And that's part of the thing you're sending.
Right.
Yeah. So if they reject it, you can then change it.
I can't find this thing. I can't find the pretty version of this. Okay, here we go. I'm doing something in a private browsing window, y'all. Actually, you know what I mean? I'm doing it in.
Always be doing things in private window.
I'm doing it in.
That's an awful nice browser you got there, by the way. You know anybody that makes that?
Here we go. Are they at RU now?
It's almost as good as Chrome.
I keep chasing them all over the internet. Yeah, especially this. No, it's not there. Okay, so anyone here seen my dark web talk about dark web? Okay, so dark web talk. Okay, so in my dark web talk, I talked about how a Nazi site called Daily Stormer receives Bitcoin receives donations via Bitcoin, and so you can actually I cannot find a freaking visualization of it right now. So on this blockchain info and some of these API sites, if you have an address, say of a bunch of Nazis on the internet, you can do a lot of transaction analysis of what's going on and all the transactions that are going into that address. And so basically, if you download the entire Bitcoin blockchain, you can find who are all the people donating to this address. And by who are all the people donating to this address, we mean what are all the pseudo addresses, the pseudonymous addresses that are donating to this, right? And so like Buddy is saying, if someone is using the same address all the time, like to get donations or to pay money, then you can start to correlate when their transactions happen with certain time zones. And you can also correlate, a lot of people leave their addresses out on public web pages and other things that can be linked to them. So you can basically go de-anonymize Bitcoin transactions, right? So if you have a starting point, like for example, an address of Nazis, you could probably go find almost everyone who's given to them.
And what they do with it, right?
Yeah.
And the IRS has an off-the-shelf product to de-anonymize Bitcoin addresses. Just as an FYI.
So in any case, that's another reason. So like the first step of that, of some of that de-anonymization is called cluster analysis. And in Bitcoin transactions, remember like Alice pays Bob 1 Bitcoin and then pays 6.1 to herself? Well, that's a change address. So there's cluster analysis where you can basically look at a bunch of transactions where an address is paying it to itself, or the same address keeps paying to these same change addresses. And so you can cluster all of these addresses and find out, okay, this is probably the same person, right? Because they're involved in a lot of transactions that keep coming back to these addresses. So you create a cluster analysis of addresses, and then the more they're reused, the easier this cluster analysis is. So that's why Buddy's saying, if you really want to be anonymous, then you have to use new addresses all the time. Now, there's also other cryptocurrencies that have, like even in Bitcoin, you can do things like CoinJoin, and Monero takes privacy a lot more seriously, and Zcash, and these others are basically built to get away from all that stuff. But yeah, so hopefully in the next 3 months, this slide deck will have more fun pictures about that. But okay, that's all I have. And it's simple.